everyone's time, so please start your presentation for 12 minutes.
Hello everyone, I'm Hyun-Chun from the All-Nighter, and today I'm going to talk about number 8, potential lines. So problem statement says that place 2 electrode into water, supply a safe voltage, and I use the voltmeter to determine the electric potential at various locations. Investigate how the measured potential lines deviate from the expectation and different condition and liquid. So my main focus are what are the relevant parameters that cause deviation, to what extent do the various experiments, condition, and liquid affect the overall formation, and how does the redox reaction contribute to the accuracy between the theoretical and empirical analysis. First, equipotential line is a series of lines that each connect multiple locations having the same electrical potential. And these lines are perpendicular to the electrical potential caused by the potential difference in ion movement for this experiment. So in the beginning condition, since I used the flash to make the solution homogeneous, as you can see that this is a concentration versus location. And as you can see that since I put the solution throughout the container so that the concentration will be constant throughout. And the blue meaning the cation concentration and the green meaning the anion concentration. But when I start to give the potential difference, it will create an electrical field. This will make the cation move to the negative part and the anion move to the positive part. So as you can see, the distribution will be more exponentially increasing as it gets closer to the electron. And theoretically, based on the Poisson equation, the theoretical ion distribution will be exponent until the end, as you can see in the blue part. However, in expectation, for my expectation, ion distribution will be rather finite and constant due to the ion size and repulsion force. As you can see that each cation is repulsing each other, and then the water molecule attached to the cation is also repulsing each other. And however, in the empirical one, the distribution will be rather decreasing due to the depletion from the redox reaction. So in the empirical ion distribution, this does not go to the equilibrium distribution, while the expectation and theoretical will go to the equilibrium distribution. So theoretical model, I used the Gauss law for electricity, where the psi representing the electrochemical potential difference, and I did the Laplacian of the electric potential difference to get the Poisson equation, as you can see over here. So this Poisson equation is equal to negative electrical charge density over the permittivity. And as we can know that in the solution container, there's only cation and anion movement to the electron, so that we can use the Boltzmann distribution to describe cation's movement and then the anion's movement. And I use the sine tilde substitute to make it simpler. And as you can see, here's a cyclobonic function resemblance. So I make another chunk of constant as alpha, and then weight it onto the sine h function. So this Poisson equation is based on the国立Chapter model, an electrostatic model at the spatial distribution of the ionosphere, but not immobilized. And this is due to the redox reaction of the electrolyte solution. And then this is caused by the accumulation and depletion that makes it unstable as it gets close to the interface of the electron. So here's a 3 assumptions that I want to talk about. So the first is the temperature is negligible. So this is the minimum temperature on my lab, and this is the maximum temperature on my lab. And you can see that there's no difference between those two when I calculate the weighting onto the sine h function. So next assumption is that ignore vertical direction of the equipotential lines in the solution container. As I make the electrode touch the bottom surface of the solution container, we can ignore that the depth of the probe does not vary the voltage measurements. The third one is the probe is of negligible length, so that the tiltedness of the probe does not matter to the measurement situations. So here's the setup. We use the DC power supply connect to the stainless electrode using the voltmeter, and here's the non-metallic container, and here's the setup for the metallic container. So how I measure it, I use the 2 identical grid paper, putting one below the solution container and put one in front of me. And then I detect the coordinate below the solution container and mark the same corresponding coordinate in the grid paper in front of me. So for the theoretical measurement, this is the Python simulation based on my Poisson governing equation. So I also properly scale the Python simulation so I can get the XY coordinate and I can directly find the voltage at the locations. So I first talk about first I want to talk about the initial experiment where I'm trying to measure where it reaches the stable parts. So that as you can see, the phase one has to take some time to create the equipotential lines. So as you can see that there's some unstable part, but it's still increasing. But when you reach this phase 2 is stable, Phase 2 because stable redox reaction and ions movement happening. However, if you go to the phase 3, multiple compounding variables happening, for example, that the product in the deposit and also the rust part of the electrode is dissolving onto the water. So NaCl solution is supposed to be transparent, but when you reach the phase 3, it looks like the yellow-brownish color. So we try in different zinc sulfates, and we also find the same phase with the stable point. So we only measure this phase 2 motion for all of my data experiments. So here's our first relevant parameter, which is the boundary conditions. So both of them are solution-contained solution, and then the left part is a non-metallic container. We also call it a Newman boundary condition, and the right part is the grounded metallic container, and this is the dielectric boundary condition. And as you can see, since the electric field is perpendicular to the metal surface, the equipotential line will be parallel to the metal surface. It makes the shape enclosed, as you can see over here. So here's the equipotential line in the pure water, and you can see we also have this resemblance for the metallic and the metallic, and as you can see, it's also a symmetrical formation due to the theoretical models. So this black scatter plot is the empirical data, where I plot onto the simulation with the same experimental conditions. And then as you can see, although it does not quantitatively agree where the location is a bit different, but then it's still qualitatively agree. As you can see that in the metallic surface condition, it enclosed always, and then in non-metallic, it's rather spread out than enclosed. So I want to talk about here, this is the pure water situation, and we can also observe a similar situation over here and here, compared with the empirical and the theoretical one. So here's the general investigation. So I first plot the 1D motion, because this is the reference for the solving the Laplacian equation. Because it's 1D and it's constant, but 2D, by doing the Laplacian of the psi, will be more easier to calculate. And this is linear because there's no dispersion of the ions in the y direction. However, when I plot the empirical one over here, as you can see the dots with the error, you can see that those are not constant, it's rather increasing at the beginning, diffusion, and then increasing at the end. And then when I try to plot the theoretical one, it's also seen as increasing at the beginning, a little bit consistent, and increasing at the end. And as you can see, although it's not quantitative here, they're quantitative and both qualitative will agree at the end, in the positive electrode side. So here's the effect of the voltage. As you can see that the voltage is increasing 1 volt, 2 volt, 5 volt, and 10 volt. There's a steep increase of the voltage, and as high enough, there's a steep voltage over here. So I want to talk about this part. So this is called the Stern layer and diffusion layer. As you can see, the steep part is the Stern layer, this is diffusion layer, and then here's the Stern layer. So Stern layer meaning that it's happening in both negative and positive electrode, but the cation are absorbed onto the interface of the electrode, and it will make the partial electrical field where the potential difference also gives the electrical field. So as you can see, here has a higher electrical field, so that the voltage will drastically increase when you look at the voltage versus location graph. And this is combining with the Stern layer and diffusion layer, we are calling this electrical double layer effect. So it's a quantitative observation for my experiments. Stern layer is usually happening in 0.0 volt to 1.34 volts, and this is happening between at most like 1.2 millimeter. So here's some threshold voltage. As you can see, if they give enough voltage, it causes a redox reaction, and it also has this similar Stern layer effect. So here's a compare with different boundary condition and different salt concentration, and as you can see there, so you can see also Stern layer and diffusion layer overall. And here's our third relevant parameter, which is the ion of the solution. So for this one, we has the concentration and different salts. So for the system, I vary the concentration distilled water 0.02, 0.01, 0.02, and 0.1 molar of the NaCl solution in the same voltage. And as you can see, the voltage, the drastic part, has the higher increase when the concentration is higher. This is because there's a more so that it makes the electrical field stronger around the electrode surfaces. So we test in different salt, which is a zinc sulfate, and this also has a similar observation, Stern layer over here, and then it's increasing the diffusion layer, and then there's also Stern layer, and when you get the enough voltage. So here's a comparison between the NaCl for the plastic and then also metallic. And also you can see there's a Stern layer, and then ions are also increased. Voltage, Stern layer, voltage point is always increasing as the concentration gets increasing. So here's an interesting observation. So as you can see, the gas is continuously forming when I use the initial solution. So is the gas emitting, and the positive side is the yellow deposit. This could be made the electrical line consistent throughout, especially for this one. If they make the deposit with a certain volume, this is metallic, so that it can shape the surrounding electrical potential lines different. So this is SEM analysis for the element we were looking forward to. And then here's the zinc stocker when I use zinc sulfide. There's also metallic deposit forming, and it's also increasing. So it will make the equipotential line surrounding here different, because metallic and the equipotential line should be in parallel. So in future work, I want to improve the limitation for the Python code, because my Python codes do not converge in the high concentration for my governing equation. And this was not able to conduct the experiment the exact same concentration. And the other limitation I want to talk about is the limitation of the国立Chapter model, where it's relatively inaccurate in solving the higher voltage circumstances. So in conclusion, although it's quantitatively not, sometimes not agree, but it's still qualitatively pretty agree between the general theoretical model and then also the empirical data. As you can see, here's a three relevant parameter we discussed with the graph for the simulation with the empirical black scatter plot comparison. As you can see that we can all agree that it's qualitatively agree with different metallic or non-metallic effect the voltage with the electrical double layer effect and also ions movement throughout with a different concentration and different type of salt. And here's some analysis account for the electrical double layer effect by improving the国立Chapter model that does not originally didn't consider about it with the depletion and accumulation consideration onto the interface of the electrodes. Here's a reference where I get the code from here, and this is a research paper about the electrical double layer effect. And thank you for listening.
Okay, so following will be the short question from the opponent.
Okay, so do you think that the main reason to cause the deviation because of the electrical double layer?
Sorry, could you repeat one more time?
A main reason cause the deviation because of the electrical double layers.
Which one caused the deviation? Sorry.
Yes.
Can you clarify? I didn't clearly listen.
What reason I cause the deviation?
So as I mentioned, effect of the voltage, different boundary condition, and ion surface concentration.
Okay, thank you. And please page 19. Did it have the boundary condition of the voltage to you can observe the deviation?
Boundary condition, as you can see, here's some aluminum. I used the aluminum foam to make the metallic.
Okay, thank you. And how many spots that you measured in your experiment?
So as you can see, there's an error. We measure 5 times, and then we
how many spots you measured the time?
5 times per each point.
Okay,
yeah.
Thank you. And did you analyze the distance of the potential line to quantify it?
But I still show you the certain layer quantification, where the certain layer happening in 1.2 millimeter.
Okay, thank you.
Of the electron.
Do you think that the equipotential lines will change by time?
Yeah, that's why I mentioned for the initial experiment for the phase.
Okay, thank
the
you.
3 phases.
Okay, thank you. And did you consider that the material of the electrodes maybe it will have it will dissolve into a liquid?
Yeah, with the SEM analysis, where we try to get SEM what elements inside.
And okay, I think next question is, did you when you measure the equipotential lines, so maybe it will cause some flow. Did you think that the flow will affect the deviation?
Yeah, so that's why we need to measure in the phase 2, where it's stable.
Okay, and do you think that each point of the depth of the voltage will not be the same?
Sorry,
Yeah, that's why we remeasure and get the error.
Okay.
So following will be the start preparation time for the opponent for 3 minutes.
这个。
Okay, the preparation time is up. So, sorry, reporter, please go back to your seat, to your stage. So, please start your presentation after. Please.
Hello, the onlookers and fellow competitors. I'm the opponent from Take Excelsior. Now I'm going to oppose problem number 8, equipotential line. Purpose statement: place the two electrodes into a water supply at set voltage and use the voltmeter to determine the equilateral potential line at various locations, and investigate how the measures of the equipotential line can deviate from your expectation. And we are mainly focused on when the equipotential lines deviate under the liquid, and how different conditions and liquids affect the deviation. And this is the opponent thinks that the structure of the solving problem may separate into first clarify the deviation which may cause, and which include the electric double layers, which may be the reason. And the second is that identify the characteristic of the equipotential lines, which may include the time time depending and also the symmetrical distribution. And due to purpose statement, we also need to investigate the equipotential lines that deviate under a different condition, like include the electrodes and liquid. And this is the strong and weak point of the order. First, that here demonstrates the iron's movement, but he now will explain how is the deviation that caused by the time of the revolution. And he had the focus on the times of the depending, but he didn't consider the electrodes influence, like a distance between the two electrodes. And second, he will explain how is the deviation caused by the liquid or another like time revolution, but he not detailed discuss about the polarities or some other characteristic of the iron. And this is the opponent thinks that need to be discussed and later is first that it will have the reason to cause the deviation from the expectation, which may include the electrical double layers, which will separate into the first layer and the second layer. And about this, the surface charge and arrangement in the first layer may be effect of the screening effect on the second layer. And also the characteristic of the equipotential line may be including the time revolution and also the symmetrical and distribution. And some parameters will affect the deviation, maybe include the electrodes and also the liquid. And electrodes maybe we'll want to discuss if it is positive or positive situation, or the distance between it may affect the deviation. And about the liquid, that is opponent wants to discuss about its conductivity and also the characteristic of the ions in the liquids. And also I want to discuss some polarities which may affect the characteristic of the liquids, and maybe some special condition like two compounds in the same liquids. And I want to mention next things.
Okay, please start your.
Okay, so what do you think that the main reason that caused the deviation?
What are the
main reason that caused the deviation? Like your question, you can explain.
So boundary conditions affect the voltage and ions movement in the solution container.
Okay, so do you mean that it is because of the liquid?
Yeah, that's why we test multiple liquid.
You will not affect by the electrodes.
Yeah, because different ions moving and they're causing different type of redox friction on the interface.
Okay, thank you. And so can you explain why we'll have the deviation from your expectation? Means that what is the definition of your expectation?
So theory, the one that I showed on sin h function, that's my theory. So I plug that into the Python simulation with the 2D file.
So it means that the expectation is the simulation.
Yeah, expectation is simulation.
And the deviation is from when you do the experiment and how is different from the simulation.
Yeah.
Okay. And as you mentioned in the short question, why we'll have the boundary condition of the voltage intensity is because that if the voltage is too low, then maybe you can't measure the maybe you can.
If the voltage is lower, are you referring to the boundary condition question or lower voltage question? Can you clarify your question?
If it is the lower voltage intensity.
Yeah. Lower voltage provided.
Yes.
Okay.
And it is because this is the boundary condition of the voltage of the voltage intensity and affect the deviation.
Okay, so first, boundary condition meaning whether the surface is metallic or non-metallic. And then when there's a lower voltage, it's still working. And then that's why Green-Chapman model is also working in the millivoltage units.
Okay, so do you think that this is the important factor that will affect the deviation?
Boundary conditions?
Voltage.
Voltage and yeah.
Okay. And about the measurement of the experiment, that you agree that as you mentioned, that the equipotential lines will change like a time depending, right?
Last part, sorry, what did you say for the last part?
The equipotential line will change by time.
By time?
Yes, it will change. Okay, so in your measure, so did you analyze the time depending?
Yeah.
And in your measurement method, then you measure the point, right?
Yeah, 1 point.
I think that the change by time is continually, right?
Right.
So can you sure that you need to change that point? How many times? How long will that you measure?
So this one is 0 minute to 320 minutes. So like about 6 hours. So can you make sure that you can catch the each point of like a voltage or electrical potential that at each part of the time? Also, I get your question. So are you saying that this is not straight? It could be like alternating? Is it your question asking?
Yes. Okay. You can say what you think.
Oh wait. Could you repeat your question? I think I misunderstood it.
Okay. And
I can answer the question you just asked. Or can you repeat one more time? I can answer the questions.
Wait, I want to change to the next question.
Okay, sure.
It's okay. And what do you think that when you put the detectors into the liquid, that it will not symmetric?
Props, when you put the props in?
Yes.
So that's why in this phase, since the props tips are metallic, all the length is negligible from my assumption, you need to wait for until it became stable point.
Okay. So did you try to use the radius of the curvature to quantify the equipotential line?
Radius of the electron?
Curvature. It's like how
curvature of the probe.
Yes.
But as I mentioned, assumption said that I see what's so. For example, let's say this is 4 volts and here's 3.9 volts. Since I assume that it's really small, so plugging this doesn't matter.
I think that the question is, did you try to measure that this equipotential line is like this? So the radius of curvature may be like this, but when the constant deviation may be changed like this, so the radius of the curvature changed like this. Did you try to use this way to quantify the deviation?
Wait, you said that radius of the probe, right? Are you talking about radius of the potential lines?
Yes.
Sorry. So that's why we put the electrode at the bottom so that we can make Z direction not curvature. As you can see, that this is the when the electrode is not touching to the bottom, so that equipotential lines can go down to the electrode. That makes it curve. But if it touches to the bottom, it's not going to curve.
Okay, so it means that you can use your ways to quantify the deviation.
Yeah, for minimize that difference.
But I think maybe you can measure this radius of the curvature of the equipotential line, and maybe you can quantify the deviation from your expectation. Do you agree?
Yeah, that's a good idea.
Okay. Yes. Okay. Then let's discuss about the effect of electron dust. Do you try to let the electron dust is the positive and the positive?
Positive and positive?
Yes.
But although there's positive to positive, potential difference meaning the both is difference.
So you think that when it is positive and positive, maybe the electrical line will difference, and also affect the potential line or not have the phenomenon.
But isn't potential difference relative, not like specifically positive to positive? Because potential difference meaning that the difference between the voltage. So I think you're misunderstanding what is the potential meaning.
But I think that when you put the electric that is positive, you still have the difference of potential. So maybe you will change the potential lines.
Oh, okay. So first, my cell, the power supply is the grounded, so it provides negative 5 to 5 volts.
Okay, I want to change the next question. It's about the distance between distance between the electrons. Do you think that when they closer, the voltage intensity and the electric field intensity will increase?
When you bring probe to the electron?
When the two electrons is closer, then the electrical field intensity will increase. But I think that maybe that you close that maybe closer, then the intensity increases. Maybe it will affect the potential or even affect the density of the equipotential line.
But then at this case, you also need to change the theoretical simulation to the sort of distance. So where you find the deviation doesn't really matter.
Okay,
the distance.
So I want to change that question about the liquid. So do you think that you say that the equipotential will change by time? So do you agree that it is because of the ions move in the liquid?
Ions moving. Yes, ions is moving due to the electrical field.
So what do you think that the conductivity affect the equipotential line deviation?
Okay, so conductivity, this is considering my Boltzmann equation, Boltzmann distribution. So as the conductivity increasing, the resistance will be decreasing. So the ion can more easily moving it, so it makes the intensity higher.
So maybe that it is the characteristic of the ions that like affect its movement, or like the discuss on what is when the mass of the ions is increases. So maybe it will move like slower. So maybe the change of the equipotential line by time will be longer.
So mass of the ions?
Yes.
But as I mentioned, it's homogeneous solution. So we mix it thoroughly and it's going to be no bulk. There's always separated.
So, do you agree that you will change by time and the balance in the final equipotential line which is stable?
Equipotential line around the final is stable?
Yeah, yes.
Wait.
First you have the first equipotential line. The final, you will maybe change a little bit, and final have a final equipotential line. Because that the effect of the ions movement or another like the valence or the magnitude of the charge.
Yeah, that's why we consider the redox reaction, the Stern layer and diffusion layer differences.
Okay, and what do you think that the liquid polarities affect? Liquid polarities.
Oh, polarity?
Yes.
Loss effect?
Because you think that it will affect the arrangement of the ions.
Right.
So maybe the change to go to the final equipotential line need to the times will be longer.
Sorry, time is up. So following is the 1 minute opponent summarize the discussion, please.
Okay, so in the first we discussed the definition about the excitation and also the deviation, and because due to the current statement, and we'll discuss it is a reason that caused by the electrical double layers, and what is the main reason to cause it to have the deviation, and in our result is because of the liquid. But also, I think the electrodes will affect the result, like a distance between the two electrodes will affect the intensity of the electric field. So the equipotentialized shape will be different. And also, we discussed some liquids characteristics like conductivity, which may affect the ions that movement in the liquids. And about some characteristics of ions, like we asked about the mass, and I think that it will affect the final times that got the
Kindly stop, sorry. Reporter, please stay on.
Okay,
And also opponent, please, later. So now is the time for the question of the reviewer to, please.
Okay, just for some clarification for the reporter, this line here seems to have reached an equilibrium.
Yeah.
So do you believe that the equipotential line reaches an equilibrium after some time?
I agree. So that's why we're measuring phase 2, not phase 3.
Okay, then can you explain the deviation, like the fluctuations here?
Also, error bar, meaning that when I measure first time 5 volts, the next one is 5.1 volts, the error bar is 0.1 volts. So remeasuring and then get the difference in between, that's the error bar.
Oh, that's the error.
Yeah, that's the error bar.
Okay, next, would you agree that all else staying constant, if the ion concentration goes up, it will be more difficult to measure the equipotential line due to the effect of double layer?
Sorry, what is constant? Sorry?
Holding all else constant. If the ion concentration is higher, the effect of the double layer will become higher.
Concentration won't be constant, it will be changing because of the ion movements.
Holding all else constant, if you change the ion concentration,
Right.
do you think the double layer will have a higher effect?
Yeah, the rate will increase.
Do you agree?
Yeah.
Does everyone agree?
I believe that the concentration of liquids maybe affect the conductivity.
Okay.
And also affect the polarities of the liquids.
Okay, thank you. Next, I want you to talk about your measurement. Did you like do your by hand, like move the probe by your hand?
Yeah.
Do you think the probe material might disrupt the ion distribution in the water in your liquid?
Yeah, that's why we need to wait until, because as you mentioned, probe is metallic, so it shapes the potential line partially. So we need to wait until it becomes stable.
Okay, so do you think there will be double layers on your probe?
No, it's
Probe
sort No, there's no power supply, power potential. The voltage is not supplied to the probes, so you cannot.
Well, you did not apply the voltage on your probe after.
Right, the third layer meaning that cation moving charge electron. A probe is neutral, so there's no way you can get.
So you don't believe there will be double layer on your probe?
Yeah.
Okay, can you turn to page 29? Can you explain why the equipotential lines here are really symmetric? They seem to have like a different.
Oh, that's why that's the problem. We didn't measure the equal number of the bottom side and the top side. So it looks asymmetric as you mentioned. But there's asymmetric.
Okay, do you think dielectric constant of the fluid will affect your equipotential line?
Yeah, that's why my crossing equation has relative permittivity and also just permittivity.
Okay, does the opponent agree with, does the dielectric constant of the liquid affect your equipotential line?
You mentioned that the liquid will affect the equipotential line.
I mean, the dielectric constant of the liquid, not the liquid itself.
Maybe you will affect, I believe.
Okay, do you think temperature will have an effect on your equipotential line as well? Can you explain how temperature affects your equipotential line?
Temperature.
Temperature, yes.
As I mentioned, temperature is negligible effect. That's the calculation over here.
Okay, that will conclude.
Kindly stop. Following is the preparation time for the reviewer for 2 minutes. Okay, it's almost done. So,
Okay,
reviewer, please stand your for presentation.
Okay, so this is a reviewer from Team Miracle. I'm John Xu. I will be reviewing the problem equipotential line. Okay, this is the problem statement, and the key points we believe are what are the deviation between expectation and experiment, and also the explanation for this deviation. For the reporter's performance, he explained how the results differ from their expectation. For their theory, they explained the deviation by using the double layer effect, the redox reaction, and Gouin Chapman model. And for their experiment, they changed different boundary conditions with different voltages and different ion concentrations. For their strength, they had good comparison between their expectations in the experiment. They had good time control. They recognized basic assumptions made, such as temperature, depth of the probe, and length. But they had some unclear graphs, and the reporter sometimes spoke too fast, which made their presentation unclear. Also, their ion concentration changes because of redox reaction, which they failed to consider. Also, they didn't mention the temperature dependency of the equipotential line. For the opponent, he summarized the reporter's presentation and also provided structure for problem solving. The pros include they brought up important points, such as time dependency, change of concentration of ions, and the threshold voltage. However, they should have discussed measurement method. For the discussion, they first discussed the main cause of deviation. The reporter said the boundary and applied voltage and electric double layer might have caused deviation. The reviewer agreed with the reporter that the main difference is caused by boundary and the existence of ion. Next, the opponent asked about the definition of their expectation. The reporter expectation is derived from simulation, and the reviewer agreed that simulating with Python is suitable to provide their expectation. Next, they discussed about the threshold voltage. The reporter said yes, they think there is a threshold voltage. The reviewer thinks there should be a threshold voltage, but the opponent should bring it up. What factors might affect this threshold voltage? Next, they discussed the time dependency. The opponent asked how long did you measure? The reporter said up to 6 hours. The reviewer said thinks that because of the long measuring time, some ions may have gathered on the measuring electrode. Next, they discussed can you use the curvature of the equipotential line to quantify the effect of ions? The reporter answered yes, maybe we can quantify the curvature difference. The reviewer thinks that curvature difference is similar to voltage difference, so we think using the voltage difference is an easier way to quantify the effect of ions. Next, they discussed does the equipotential line change with time? You should consider the ion time to change the ion migration rate. The reporter answered that yes, they did consider this. The reviewer thinks the ion migration rate determines the voltage change and the time it takes to reach equilibrium. And since temperature affects the migration rate, we think the reporter can make it a variable. This is the points missed. They missed some relevant parameters such as electrode shape and material. Also, they missed whether the equipotential line reaches. Ignore that. And next, they missed the effect temperature. They only said that in their assumption, they calculated that their experimental setup, their temperature doesn't really affect, but they didn't say whether big changes in temperature will affect their equipotential line. And also, they missed the effect of probe material on ion distribution and equipotential line. Also, they missed the motion of measuring may disrupt the ion distribution in their liquid. And lastly, they failed to acknowledge the chemical property of the measuring probe. Thank you.
Minutes conclusion remark of the report.
Okay. So I want to say that there's a 3 relevant parameter we test, which is the metallic and non-metallic boundary condition, effect of the voltage, hours of solution by changing the concentration and different type of the salts. And then, as you can see from the graph and then also simulation and empirical black scatter plot, there's still quantitative agree between the general theoretical trend and experimental data trend. We also talk about analysis about account for the electric double layer effect, where the cations or anions are attached onto the electrodes interface, and it causes redox reaction, depleting or accumulating the ions, so that the ions will not reach the equilibrium distribution. And then for the discussion, we talked about the main reason for the deviation, and I said in this 3 relevant parameter, Neumann and the electric voltage and ions are the main cause for the deviation. And then we also talk about experimental points are plot onto the theoretical graph, so that we can compare those differences between the expectation and also the empirical data. We also talked about the voltage and boundary condition are important, as I declared that the boundary condition just meaning that whether it's metallic or non-metallic. And we also talked about measurement over time. So I mentioned that we are trying to minimize, we understand that there's time makes it flow and differences, and there's also confounding variables. So we are trying to find the stable phase and trying to measure the voltage over this period. We also talked about the probes and negligible lengths, so that we also wait until the number became stabilized in the voltmeter. And then we talked about curvature, however, we put electrode touching onto the bottom surface, so curvature is less consideration for my theory. Electrode with the positive and positive electrodes will give the potential difference, so that it will still have the power supply. And for my experiment, my DC power supply is the grounded. Experimental distance between the electrode, which is really good idea. I think I can use it for the future works. And then ions move in the fluid, and we also talked about the mass of the ion, but then my solution is homogeneous solution, so it doesn't really matter. Thank you.
Okay, time is up. So next I would ask all three presenters to stay on the stage and ready to answer the questions from the jurors. So any questions? Oh, please.
I see the assumption 1. The temperature dependent, and your calculation tells us 99%.
Yes.
Doesn't change too much.
Yes.
So you think this is assumption that temperature
Yeah.
will not affect your
Yeah. So it's because we need to measure some certain time, and it could be varying in the lab, so we try to measure it.
I'd like to have opponent and the reviewer comment on this result. Comment. I think the reviewer mentioned about the temperature dependent, right? And also opponent also mentioned the temperature dependent.
Okay, I read that the temperature will not directly affect the deviation of the equipotential line. The main reason is like the liquid, like the concentration or the polarity.
As you can see, they only calculated these up for 18 and 22 degrees. And I think if the temperature difference is larger, there might be more deviation.
What's your point?
Yeah.
So if this one can be ignored, that means something higher than, much higher than 10 to the 15 or 16 power.
Yeah, I understand that if the number gets bigger, the percentage could be underestimated because I only round up to 360. Although we try to get, we only use 360, the argument is still that after that, the number will be smaller contribute to the overall number, so that the ratio will be still similar in overall.
Questions? Yeah, please.
If you stir the water, what do you expect the equal potential line to change?
If you stir,
It will be deviating at the beginning, but then due to the electrical field, it will become more stable at the end due to the electrolysis.
it's okay.
Stir one way or the other way, where the equal potential line will be different.
Yes.
You expect answer from others?
I believe that depends on how you have stir the ion distribution in the liquid. So if you stir it this way and that way, that might have different effects on the ion distribution in the liquid. Thank you.
I believe that when you stir, may even affect the ions that in the liquid, so it will cause some deviation of the equipotential line.
Please.
I have one question to the reviewer. So
why it is important?
I think, yeah, like the chemical potential is like the only you're actually measuring like the electric potential and not the chemical potential in the liquid. So the chemical properties of the electrons will matter.
Okay, seems there's no further questions, so we move on to the scoring part. Yeah, please.
Okay, interesting. Okay, here we fine. When you do the simulation, you use the formula is in open space.
Yeah. No. We use the boundary.
How do you define the boundary? And the boundary between your experimental boundary,
Yeah.
the same?
Yeah, we get the exact size of the simulation with the meter units.
Tensor height.
Yeah.
The area is very, very high, right? I mean the boundary here.
One more time, sorry.
Here your boundary
Yeah.
has a very high barrier,
Yeah.
right?
Yeah, it's.
But when you do an experiment, the barrier are the same as you simulate.
Yeah.
The same. How do you know the boundary?
Oh, that's why we only consider 2D dimension x and y. Yeah. Yeah. Oh, yeah, they will be conducted. Yeah.
I see the alumina foil.
We use the dielectric boundary conditions, which say that the voltage is 0 at the metallic surface. Yeah.
What is 0 at the metallic surface?
Yeah, V equals 0 onto the metallic surface.
Okay, those all jurors finished their scoring. So I would like all the jurors to raise your score for the reporter. The scores are 7, 6, 7, 6, 8, 8.
Thank you.
And the scores for the opponent is there are 7, 8, 7, 8, 9, 6, 8, 7, 6, 8, and 8. The score for the reviewers scores are 7, 7, 8, 8, 9, 8, 8, 8, 8, 7, and 8. Thank you. So, we have a little bit distribution for the opponent. We have a 9 and 2, 6. So, any comments from the 9?
I think 9 is very simple. I think their presentation province. And someone reminded me that this kind of experiment was done in the high school or in the middle high school or high school. Okay, so I think they've done pretty well and they got experience. Most important, they have simulation. And the other two teams, they're crashing. They're asking very fundamental questions. I think that's also very good. Thank you.
Okay, we got the 2-6. So any comments from the 6?
On my 6. So for the opponent, I think the 6, the most scores reducted from me is that during discussion, so you ask too many questions, but I mean, not half of the time you are asking questions, but and this is not this. Let me put it this way: half of the time you are trying to do is question and answer, and you got the answer, but there's no opinion from you, so we don't know why you ask these questions and how does they bring us to more understanding for the topics. So therefore, that is therefore I subtract some points from me. Additionally, so from your presentation, that it didn't show enough the understanding of the report. So for the first column of your speech, that got a little bit lower grade from me. So to sum up, then you got 6. Okay.
So I think that's a 6 for the opponent, right? So you want to give a comment for your 6 or?
Yes, for the report. So he emphasized his temperature is significant, but we know that his electrolyte is solubility, for example, is strongly temperature dependent. So the nature survey these different kind of electrolytes. So I think that's one question. The other thing is his presentation. For example, his distribution of potential. I think it would be much easier to realize in this 2D form, not just in this 1D form. And then the consideration of this boundary condition, I think is very good. But I think the presentation overall is speaking very, very fast. I think that's probably not very good. Yeah.
So we've got also 2-6 for the opponent. I think Professor Law already gave a comment to the opponent. So any comment about the opponent 6? Reviewer, the score is relatively even, so I think there's no need for further comments. I would like to announce for another break, so please come back in 10 minutes. 因为他们最高，他走来走去，现在不方便，除非是要用你的，那你假如是因为像我这个像我这一个，如果是调到负10，这个要到50块以后。知道，所以你刚讲我在想说，基本上，
看像当时就是
大家跟口口。
这应该是65，记得是65。这个他可以，他说20瓦。
那这种是办活动比较方便，
不用拉线拉的那么那个。
因为它提供110瓦，110。 最起码要把那个。觉得真的要做，这个有机会做。
但是我怕它会有个机率检测，检测设备，其实怕它进不进去，因为它都会有。对，没有错，但是。而且它那个机械机的是，所以你如果放在电子要长时间用，它就受不了。因为你成绩。
It's time, so please step up to your seat so that we can start the third round. Everybody's ready, so we start our last round. Physics 5 in this morning. The reporter will be Alsacian. Opponent is Miracle. Reviewer is all-nighter. The problem to be reported is so we start for the preparation time of 5 minutes. Okay, it's almost time, so reporter, please start the report. You have 12 minutes.
Hello, honorable judges and fellow competitors. I'm a reporter from the Associate, and today I'm going to report problem number 10, droplet explosion. This is a problem statement. When a drop of a water mixture is deposited on the surface of a hydrophobic liquid, the resulting drop may sometimes fragment into smaller droplets. Investigate the parameters that affect the fragmentation and the size of the final droplets. And my main focus will be, first, what caused it to explode? Second, how do different parameters affect the size and the time scale of the model droplets? And how do different parameters affect the size of the final droplets? And here is my outline. This is an observation video. The mixture in the left video has a higher concentration, so it is going to fragment. But the mixture in the right video won't. Therefore, we found that the concentration will affect the fragmentation the most. That is, the mixture needs to above a certain concentration to fragment. I'm going to talk about the qualitative explanation. First, I'm going to talk about the definition of the fragmentation. And we will define this droplet as the model droplet and the radius of it. And its temporal evolution will be first expand, then reach a maximum radius, then will start to shrink. And during shrinking, the droplet will eject into many smaller droplets. So we define this process as the fragmentation. And the time spent to finish the whole process will be defined as the explosion time. And I'm going to talk about the physics behind each phases. First, the droplet was dropped onto the surface of the oil, so the droplet flattens. As the gravitational force pulls the model droplets downwards, the surface tension won't be strong enough to remain it as a spherical shape. So it will tend to shrink from the spherical to like a plate. And since the droplet was flattened, so the thickness at the rim here will be thinner than the center. And because that, the alcohol evaporates faster than the water, so the concentration at the rim will be lower than the center, which means that the fraction of the water at the rim will become higher than the center here. And because that the surface tension of the water is higher than the alcohol, so because that the fraction here at the rim is larger than the center, so the surface tension at the rim will be larger than the center. And the surface tension gradient will trigger the net force from lower surface tension to higher surface tension area. And it's creating the magnetic flow, which causes the model droplet to expand. And then the model droplet will stop at the maximum radius. It will because the system will tend to minimize the surface energy. That is because that when the surface tension of the air mixture interface plus the oil mixture interface is lower than the oil-air interface, the mixture will increase its interface area to reduce the surface energy. But when the surface tension of the air mixture interface plus oil mixture interface is equal to the oil-air interface surface energy, the droplet will stop spreading and reach a maximum radius. And since the critical concentration will stop the spreading, so the concentration at the rim will be the critical concentration, which means that it is the boundary concentration. And to reach the lowest surface energy, the rim needs to decrease the surface area, and we will turn its edge shape from the smooth shape to the shape like fingers. And due to the same situation, the fingers will inject into many smaller droplets, and this process is called the plateau relay instability. So, and the final droplet is defined as the droplet that the model droplet resolves into, and the size are measured instantly after fragmentation. And I'm going to talk about the qualitative theory. Through our literature survey, we found these empirical equations of the characteristic radius, which has positive correlation with the maximum radius, and the time scale, which has linear relation with the explosion time. Therefore, we are the concentration, the thickness of the oil, and the volume of the model droplets will affect the radius and the time scale. So we are going to discuss these parameters and build theoretical predictions with the fitting constant with the relation between the maximum radius between the exact number of the maximum radius and time with the scales. And this is our experimental setup. We fill the soybean oil in the petri dish and we put it on the plate to remain the temperature of the oil. And after that, we cover the whole system in the plastic board to avoid the environmental infection. And here's our measurement. We measure different volume evaporation flux under different mass fractions in order to collect the data for our theoretical model. And here's our experiment about the boundary concentration. Through these two graphs, we found that only the fraction of the alcohol of the mixture will be the boundary condition. And the boundary concentration will be around 0.65 to 0.67. And I'm going to talk about the experiment about the initial concentration. First, I'm going to talk about the explosion time. To reach a critical mass fraction, higher concentration will need more time to evaporate. So the explosion time will have positive correlation with the mass fraction of the alcohol mixture. And when the time increases, so the model droplet will have more time to expand. So the maximum radius will increase when the mass fraction increases. However, the size of the final droplet will decrease when the mass fraction of the alcohol increases. It was because when the maximum radius increased, the time at the outer part of the model droplet will become thinner. So the size of the final droplet will decrease. And I'm going to talk about the experiment about the volume of the model droplet. Larger volume of the droplet will need more time to evaporate, which means that the explosion time will have positive correlation with the volume of the model droplet. So do the maximum of the radius. But as you can see, the increase of the maximum radius will be abated. It was because when the volume reached a certain number, the droplet will be too heavy for the surface tension to pull it outward. So the increase of the maximum radius will be abated. And the size of the final droplet and the volume of the model droplet will have positive correlation. It was because when the increase of the maximum radius is abated, the redundant volume will be adding on the rim of the model droplet. So the size of the final droplet, which has a positive correlation with the size of the fingers, will increase when the maximum radius increases. And the last experiment is going to talk about the thickness of the oil. The marinating flow between the mixture and the oil will trigger the oil beneath to flow along. And because the viscous effect of the oil, it will cause energy loss and create a boundary layer to flow from the center to the edge. And due to this motion, it will also create a pipe flow to compensate the boundary layer. And since the thickness of the boundary layer is fixed, so when the thickness of the oil decreases, the thickness of the pipe flow will decrease. And when the thickness of the pipe flow decreases, the pipe flow will need to have more velocity to compensate the boundary layer. But since the energy is limited, so the system will need to reduce its speed. That is why the explosion time will increase. And when the thickness of the oil decreases, the flow velocity of the system will decrease. So the alcohol will evaporate before it spins outward. So the maximum radius will decrease when the thickness of the oil decreases. And since that maximum radius will increase when the thickness of the oil increases, so the rim at the outer part of the model droplet will become thinner. That is why the size of the final droplet decreases. And the relation between the size of the final droplet and the maximum radius will be negative correlation. But this graph is not obvious. I will explain it in the next session. And I'm going to talk about the unified data analysis. Through these three graphs, we can find that the evolution of the radius of the model droplet can be described with the scaling law, which means that after standardized, the trend will be the same. And if we analyze the relation between the maximum radius and the model droplets and the size of the final droplets, the trend will be the same, which is negative correlation. And we can see that when the parameters is the thickness of the oil, the trend will be negatively correlated as the same as the concentration parameter. And here's my conclusion. First, we found that the fraction of the alcohol in the mixture will be the only boundary condition of the experiment, and the boundary concentration will be around 0.65 to 0.68. Because that the surface tension of water is larger than the center, so the surface tension gradient will trigger the magnetic flow, then the molar droplet will start to expand. And the surface energy difference between the different interfaces will stop the expansion when the molar droplets reach the maximum radius. And to remain the lowest surface energy, the ring will need to decrease the surface area. So will it turn to its S shape from the smooth shape to finger shape, then eject into many smaller droplets. And in our first experiment, we found that the mass fraction will be positive correlation with the explosion time, maximum radius, but however, it will be negative correlated with the size of the final droplet. In our second experiment talking about the volume of the molar droplet, we found that it will be both positive with the explosion time, maximum radius, and also the size of the final droplet. And in our last experiment about the thickness of the oil, the thickness of oil will be positively correlated with the explosion time and the maximum radius. However, it will be negatively correlated with the size of the final droplet. And these three graphs shows that the evolution of the radius of the molar droplets can be described by the scaling law, which means that after standardized, the trend will be the same. And if we analyze the relation between the maximum radius and the molar droplets, of the molar droplets and the size of the final droplets, the trend will be the same, which is negatively correlated like this. And this is my report. Thank you for listening.
Okay, thank you for your presentation. I just have to clarify. You used ethanol and water mixture throughout all of your experiments, am I correct? Ethanol and water.
Can I rephrase the question again?
You used ethanol and water mixture throughout your experiment.
Sorry, I can't.
What droplet did you use? Ethanol and water mixture. You used ethanol. You used alcohol.
Yeah, I used alcohol mixture.
Okay. Okay. And you didn't change the type of the liquid for the droplet?
Yes, we changed the type of liquid in our experiment, but the data it will be difficult to analyze.
It's difficult to analyze. Okay, thank you. And the problem statement says that the surface has to be hydrophobic. Can you explain why it has to be?
Because that the hydrophobic will have the viscous effect, so it will cause a magnetic flow because of the surface gradient.
So it's because of the viscous effect of the.
I mean, if the liquid is hydrophobic liquid, the mixture will flow on the surface of the liquid.
Oh, so it's just for it to flow on the surface?
No, I mean after the flow on the surface.
Yes.
The surface tension gradients will cause the magnetic flow and the boundary layer of the hydrophobic liquid.
So it's the surface tension that matters?
Yes.
Okay, and why did you use ethanol? And why did you use alcohol? What's so special about the chemical properties?
The first reason is because that the alcohol will be mixed with the water, and the second reason is that the alcohol will evaporate faster for the observation.
So you think there are only two reasons why you chose alcohol? The first one is that it evaporates faster, and the second one is that it mixes with water.
Yes.
Okay, and have you considered to analyze from the energy point of view how the alcohol influences the spreading?
You mean if I analyze
energy,
the surface energy, or
yes or no?
No.
Okay. And next question. Do you have any explanation of how? Okay, thank you.
Following is the preparation time for opponent, 3 minutes. So it's almost time, so opponent please take stage. You have up to 4 minutes for presentation, please.
Okay, I'm Arthur Chung from Team Miracle, and I'll be opposing problem number 10, droplet explosion. So I'm sorry about this. The problem statement says that when a drop of water mixture, for example, a water alcohol, is deposited on the surface of a hydrophobic liquid, and the resulting drop can sometimes fragment into smaller droplets. Investigate the parameters that affect the fragmentation and the size of final droplets. So we think the key points are, why does the surface have to be hydrophobic? And what causes droplet fragmentation, and what parameters influence the size of final droplets? And here's the overview of the report. For the phenomenon, they demonstrated that the droplet spreads out and forms small particles and shrinks. And for the theory, they use the evaporation rate to explain the American flow, and they use surface tension to explain why the radius of the mother droplet changes. And they use the instability to describe the finger shape that is produced. And for their experiments, they change the concentration and they observe the effect of it on the mass radius and the time scale of the mother droplet. And for they didn't show this. They didn't change the was observed for that. They did experiments on types of droplets, but they didn't show the experimental results. But they did find a boundary condition that produces the daughter droplets. And here are the most empirical graphs explaining the phenomena and with time measurement. But for the cons, they have an unpersuasive theory, and as I will explain in my discussion, they do not explain the choice of the liquid, which is alcohol. They do not show the experiment of changing the droplet type. And they lack explanation for the instability, and they have faulty explanation for why ethanol produces Maragoni flow. So here are the points to be discussed. For theory, I'd like to discuss how hydrophobic your vegetable oil is and its influence on this Maragoni effect and its concentration gradient necessary for spreading. And then I'd like to explain the fractional Rayleigh instability, that is the fingering of the finger shape of the mother droplet, and use the energy point of view to explain how this forms and what influence the size of the final droplets, which are not very clearly explained in their presentation. And yes, and as I previously stated, I'd like to explore this phenomenon from the energy point of view and introduce why the surface has to be hydrophobic. Also, I would like to discuss the shrinkage of the mother droplet, and for their experiments, I'd like to hear their explanation for the radius of the mother droplet versus the size of the initial droplet, and how the shape of the droplet boundary influences the phenomenon. So I'd like to begin my presentation. So you stated that you chose alcohol because it mixes with water and because it evaporates faster. But have you considered its chemical properties? For example, it is both hydrophobic and hydrophilic.
We have considered that in our experiment, but when alcohol is mixed with the water, it won't be hydrophobic.
But it is. Do you agree that ethanol acts as a surfactant between water and oil because it mixes with both?
Can you explain?
Ethanol mixes with oil and water. It acts as a surfactant, so it helps the water and oil mix. Consider the effect of ethanol as a surfactant?
If we need to consider in our experiment, we need to because as the alcohol will evaporate before.
So you haven't considered it.
We have considered it, but because the alcohol will evaporate before it's mixed with into the oil, so
evaporate between it touches the oil.
So you mentioned that the alcohol will mix with the water and the oil at the same time. But the alcohol mixture will evaporate and going to expand before the alcohol in the mixture mixes into the oil.
So I'm not talking about mixing, I'm talking about the ethanol is still in the droplet. Okay, can you come to the whiteboard? Okay, so
The reason why ethanol is both hydrophobic and hydrophilic, the chemical structure of ethanol is this. Yes. So this part allows it to mix with the oil, and this part allows it to mix with the water.
Yes.
So when this part mixes with the oil, the energy actually decreases. And when this part mixes with the water, the energy decreases as well. And your explanation, for any system, the energy it tries to reach its minimum, am I correct? The energy tries to minimize itself.
Yes.
So that's why the droplet spreads out. So this is the problem.
But as I mentioned, that is my answer. The alcohol will evaporate before this part of the alcohol mixed with the oil. So
I'm not going to mix it.
I know. This cannot. I mean, we don't consider it this experiment. So we didn't consider it.
You don't consider it?
No, we didn't consider it.
Okay, and I'd like to ask you: does the energy increase? Or does it decrease? Does the energy
decrease?
Energy
because that's the mercury flow between the mixture and the oil will like this, and the energy will give the mercury flow energy. So when
you just said that the mercury flow will give the droplet
surface tension will give the mercury flow and energy to cause the droplets expand and eject outward.
If the mercury flow is adding energy to the droplet, how does this energy decrease?
I'm going to explain it, please. Okay. Ask this. Okay. Please. When the mercury flow causes the eject droplet outward like here, this,
yes.
And because of the viscous effect of the oil, as I mentioned in my report, the viscous effect will cause energy loss. So when it's moved outward, it will cause energy loss. Then so it will stop.
You're saying that the viscous effect takes energy away from the system. What happens when the surface is not viscous? You're saying that if the surface is not viscous, the droplet will not spread out because the energy will not increase?
I mean, every will have the viscous effect to cause the boundary there and the high flow. And because of
the viscous effect that takes energy away.
Yes.
Okay, but if we just consider the droplet, well, its energy is proportional to the area times its surface tension, am I correct? The energy of this droplet is proportional to its area times its surface tension. This surface tension may be a function of distance, but it is proportional to the area and the surface tension.
You mean that the energy of the droplets has the...
Yes, I'm just asking what the energy of the droplet is proportional to. It is proportional to the area and the surface tension. That is that is the definition for surface tension. So when the droplet expands, doesn't the area increase? And because ethanol is evaporating,
no, the area doesn't increase, but it means that the droplets of the smaller droplets of the area of the model droplet has to eject outside. So
yes, but if you take all of the droplets into account and treat them as a system, the energy of the entire system will increase or decrease?
Decrease.
And then because of viscous flow.
Yes.
Okay. But if there's no viscous flow, and if there's no viscosity, this will still spread. And when this spreads, this area increases. And when this area increases, the energy increases. But if you consider the chemical property of ethanol, you can explain why you want it to spread. So as I just explained, when the area increases...
But since we didn't consider this...
let me explain. Thank you. This part wants to mix with the oil. And oil is hydrophobic.
Yes.
When this part mixes with the oil, its energy decreases. And if we don't consider the interface between droplet and the oil, then the energy of this system actually increases when the droplet expands. But when we consider the interface between the oil and the droplet, because there is more surface for the ethanol to contact the oil, the energy actually decreases because it because the ethanol in the droplet comes into contact with the surface.
Yes.
You agree? So may this be able to explain why the droplet wants to expand instead of the viscous flow, which I think
the droplet will tend to expand is because of the surface tension.
Yes, but the surface tension is related to the energy, and if we just look at the energy, we can very intuitively explain
This explain why the smaller droplet will be stopped at the outer part of the power droplet. So we need to.
This may stop because I think there will be a dent caused by this, and there will be a dent in the surface caused by this, and these may come to equilibrium. But do you agree that because ethanol mixes with oil, it makes the mother droplet want to expand?
No, it won't. I just mentioned that before, that we don't consider it because that when alcohol during its expanding, the smaller droplet will tend to like the water, right? Yes. So the surface tension of the smaller droplet will increase, yes. And because the surface tension of the small droplet increased, and the energy was an energy loss caused by the viscous effect. So the smaller droplet after evaporation and extracting will stop at the point please flip to page 3.
Okay, I'm not talking about why the smaller droplet would stop. I'm just talking about why there isn't there only flow outward.
So I want to explain because I think this can don't be considered in the experiment.
So you're saying that it expands because there's viscous force, and that viscous force allows the energy of this to decline. I don't understand.
The viscosity.
Okay, let's move on to another discussion because let's look at another observation of energy here. So as I said, when the droplet comes into contact, when the surface between the droplet and the oil is larger, the chemical property of ethanol allows the energy to increase. And do you think that will be able to explain the amount of final droplets and the size of final droplets as a function of the concentration of the initial drop? If the concentration of ethanol for the initial drop is larger, in your experiment, you observe that the final droplets are smaller or larger? So if the concentration for the initial droplet increases, does the size of the final droplet increase or decrease?
Experiment about initial concentration 23, please. This one, it will increase.
Yeah, increases. Yeah. Mass fraction of the ethanol. So, what's your explanation for that?
Because that's the maximum radius will increase when the fraction of the alcohol increase. So when the maximum radius increase, the ring at the outer part of the molecule will become thinner like this.
Yeah. Also, it's because the outer part is thinner, but how does the thinner?
Because then the size of the final droplet will has the positive correlation with the
thickness.
I mean the size of the final droplet here, not like this. The final droplet is like this, and the size of the final droplet will has positive correlation with the figures that's here, pictured here, as I mentioned in my report. And because that, when you have the same volume, it's expand outward, and the ring here will become more thinner and thinner. So the size of the final droplet will decrease when the mass fraction increase.
So do you think that when because the ethanol wants to come into contact with the oil, so it forms these droplets because it creates more surface for the ethanol to come into contact with the droplet. So we think this will be able to explain, using the viewpoint of the energy, we can explain the size of the final droplet when the concentration is increased. Do you agree?
Yes, I agree.
Okay, thank you. So in our discussion, we asked the reporter why does the
sorry, now you are going to do the summary.
Yes.
Okay, please start.
So for the summary, we asked the reporter why does the surface have to be hydrophobic, and the reporter said that it just provides a viscous force, and that counters the expansion of the droplet. But we think that is because ethanol can dissolve in oil, and making the surface hydrophobic actually allows the energy of the system to decrease when the mother droplet expands. And I think that is a more intuitive explanation than the reporter said. And also, we discussed whether the energy may be able to explain the size of the final droplets, and for the reporter is that the size of the final droplets is influenced by the size of the daughter droplets is influenced by the size of the mother droplet, but we think that the size of the daughter droplet is influenced by the energy minimalization, that the ethanols will be in contact more with the oil.
So, reporter, please go back to the stage. Opponent also on the stage. Opponent, please, ready to answer the question from the reviewer. The time is 3 minutes, please.
Do you think the alcohol evaporation rate is uniform across the rim of the droplet, the mother droplet?
You mean the evaporation rate is?
Yeah, is it uniform across the rim radius?
Yes.
Okay. And then also, what measurement method did you find the droplet radius is?
What?
Measurement method.
Yeah.
How did you measure?
We have filled the alcohol in the place, and we measure the mass decrease and of the time.
Right, but how did you measure the radius? How did you measure the radius?
After measure the evaporation rate, we will use the equations to calculate the evaporation.
Okay, that's okay. And then also, do you think it seems like they didn't provide a maximum or minimum concentration that they should determine? Do you think that's something you should pay?
They did determine the boundary concentration.
Okay, so you think that's an important thing to consider?
Yes.
Okay, good. Okay. And then also, after the Marangoni effect finishes, do you think the inner droplets have the same mixture concentration as the peripheral droplets?
The concentration of the mixture at the center will decrease when the time passes, but the concentration at the rim of the mother droplets will remain as the rainfall concentration.
And then they didn't explain a lot about the experimental cell, but do you think that maintaining the drop height is very important?
Yes.
Okay. And then also, it seems like you didn't really talk about water evaporation. Do you think that's something you should consider?
The water evaporation will be considered if we need to investigate how well the radius of the mainly outer part of the mother droplets. So we didn't consider in this experiment because that we need to investigate only the alcohol mixture is in our way.
Okay, that's okay. And then also, it seems like in your experiment you use food coloring, is that correct?
Yes.
Okay, do you agree that food coloring, if added in, would change the concentration?
We only add a drop of the food coloring, so we think it won't affect the surface action.
So you think that volume is negligible compared to
yes.
The whole? Do you think that the food coloring will affect the concentration, the initial concentration?
I don't think it will affect the initial concentration much, but it will definitely influence the surface tension and energy.
Okay. And then also, have you tried to use other types of oils or other surfactants?
Yes, we have tried to use other types of oil, but since that the soy oil will be the easiest hydrophobic liquid for us to observe, so we use the soybean oil.
Okay, thank you.
Okay, time is up. Reviewer, you have 2 minutes to prepare your presentation. Okay, it's almost time. So, reviewer, please present your 4 minutes, please.
Alright, thank you. So my name is Justin Wang, and I'm representing all nighters to review number 10, droplet explosion. Alright, so this is the problem statement, and then for us, I think the main focus should be what parameters affect the fragmentation of the droplets, and also how many and what are the sizes of the final droplets. And then so for the reporter, I think that they explained the phenomenon pretty well because they talked about how the water and alcohol mixture onto the oil will become smaller droplets, and then they also provided some theories talking about the surface tension gradients, and then they also talked about some of the parameters they tested for the experiments. And then some pros are that they they showed some demonstration of the videos, and they also provided some good parameter tests. However, there were also various cons that they should consider as well. For example, their experimental setup is a little unclear, and then they also assume that the alcohol evaporation at the rim is constant, which may not happen. And then also, they also need to consider, they also need to emphasize how they measure the exact radius and also the height of their rim boundary layer. And then they also did not account for various temperature differences. So for example, like the mixture and also the droplet may be different. And then they also lacked a lot of derivations of the equations, and then they also didn't account for some of the initial alcohol evaporation, like and the food coloring influence. Okay, and then for the opponent, they summarized a lot of various points. For example, how they need to talk about the hydrophobic surfaces, and then the necessity of concentration gradient, all that kind of stuff. And then they also talked about the plateau related stability. And then they asked various relevant questions to the reviewer, and then mentioned various points to the reviewer that he might have missed. Okay, and he also had various cons though. However, for example, and he also repeated a lot of questioning on the same topics, such as energy. Alright, so for the discussion, first they talked about alcohol as a surfactant, and then how they also mix with oil as well. However, I think that the alcohol is both, while it is both a hydrophobic, it has hydrophobic and hydrophilic properties. They're talking about the same thing, but then it's just that the location is different. And then they also talked about energy change, and the reporter talked about how you have to consider the surface tension that provides the energy for the droplet. However, I think that the viscous effect should be considered. However, the reviewer agrees with the opponent that surface area increase may decrease the net energy for the droplet flow. And then they also talked about changing concentration of the alcohol. And then for me, I think the reviewer thinks that the final droplet size will be smaller as well because the faster expansion in the total surface area. But then at the same time, there will be more fragmentation as well. However, there were a few points missed that they need to actually address. For example, the reporter needs to talk more about derived equations, and then they also need to account for initial experimentation like water evaporation and alcohol evaporation prior to the experiments. And then they also need to consider things like drop height in the experimental setup. They also need to test on, for example, other mixtures like soap and hydrogen peroxide, things like that. They also need to account for, like for example, fluid shear stress, temperature, and then also the velocity later on. Thank you.
Okay, time is up. So following is the remarks of the reporter for 2 minutes, please.
This is my concluding. The surface tension at the outer part, at the rim of the model droplet will has a higher surface tension. So the surface tension gradient will trigger a membrane flow, cause the expansion of the model droplet. And the surface energy difference between the different interface will stop the expansion of the model droplet. So the droplet will stop at a massive radius and start to eject into more smaller droplets. And to prevent the low surface energy, the rim will need to decrease the surface area. So we will switch to shape on smooth fingering and eject into more smaller droplets. And the final droplet will be defined as the droplet that the model droplet stream soaks into. And here's our result of all the experimental data and analysis. And the mass fraction will be positively correlated with the explosion time, mass and radius, but it was negatively correlated with the size of the final droplets. And the volume of the mono droplet will be positively correlated with the explosion time, mass and radius, and also the size of the final droplet. And the thickness of oil is positively correlated with the time and mass and radius, but not the size of the final droplet. And the radius evolution can be described by the scaling law. And the mass and radius of the mono droplet is negatively correlated with the size of the final droplet, but the trend won't be upwards. And here's the remark. The alcohol, the remark about the alcohol is that when it's mixed with the water, it will be the hydrophobic liquid, so we can don't consider it will mix into oil. And the surface tension energy, it would be considered in the experiment, but it only will be considered that the surface energy will tend to be the lowest. And when the mass and radius increase, the final droplet will decrease. The concentration of the center of the mono droplet will decrease. That it will evaporate after time passed. And the addition of the blue color is very little, so it will not affect. And the blue color.
Thank you. So following is the time to answer the question from the jurors. So I would like to ask all three teams to stay on the stage. Okay, so any questions, please?
I would like to ask all of you, when a fragmentation occurs, what the surface energy and the surface area changes, increase or decrease?
You mean when the fragmentation occurs, the surface energy will decrease or increase?
Surface energy.
We think that the surface energy will only tend to be the minimalized, will be the
increase or decrease?
Decrease.
And area? Area of
the mono droplet, or area of the mono droplet will decrease.
Area of the droplet decrease.
Yes.
Okay.
The energy decreases and the area it comes into contact with the oil increases.
And then the energy, I think the energy decreases as well, and then the contact decreases as well.
I have a short question for all three of you. I'm asking that if the evaporation of alcohol is, without any change of other properties, but without evaporation of alcohol, what will happen? Will the result change?
Start from who?
Reported. The reporter believes that the evaporation rate will be important to the experiment because that's the evaporation.
No, answer. If evaporation, no evaporation.
If there is no evaporation,
yeah,
it won't cause the surface tension gradient of the droplets.
Okay.
The size of the mono droplet wouldn't increase as quickly, and there will be less fragmentation.
If there is no change in the concentration because of concentration, therefore there's no change in your surface tension, and so it won't occur.
Any further questions? Yeah, please. The question says it may sometimes fragment into a small droplet. So any situation it will not happen.
When the concentration is below the critical concentration, the droplet won't eject into smaller droplets. So
concentration of what?
The concentration of the alcohol mixture. is below the critical concentration.
So what's the critical? You know the number or not?
It depends on different mixtures.
It's okay.
We agree with the reporter that the concentration alcohol influences whether it will fragment to smaller particles or not because of energy minimalization. And the concentration of alcohol is also determined by the rate of evaporation. So we think that should what?
Yeah, I think there is a minimum concentration and maximum concentration of alcohol that should be considered, and if it goes over or under that, the phenomenon may not occur. And also, if you change alcohol types, then the phenomenon may not occur because of the intrinsic bonds.
Yeah, please.
The reporter in his report has emphasized many times the scaling law. So I will ask all of you, can you comment the scaling law indicates any physical concept or idea?
So your question is what's the concept? What's the physics concept of the scaling law?
36, please. 36.
Yeah, please in short. Please answer.
When the parameter is the max function, the trend won't be like positive deviation. It was no problem. But when the oil thickness decrease, it will decrease or increase. It may cause some deviation because of the energy of the oil or the surface tension. And when the parameter is the volume of the droplet, it will be affected it will have deviation because that it will be affected by the gravity force.
It's okay.
So we think we still have to go with our explanation of energy minimalization. So for example, when the initial concentration is higher, maybe according to this graph, the mother droplet will need to expand to a larger radius and to achieve its minimum energy. And we also think that the scaling law does not apply to every single situation because you can see that the shape of the lines are different.
Similar to what the reporter said, the scaling law, if you change, for example, the initial concentration, the volume, that kind of thing, the radius will gradually increase but slowly decrease over time as well.
Okay. So if any further question? So if there's no further question, we move on to the scoring part. All three of you stay on the stage to see the score. Okay, so please all jurors raise your score for the reporter. The scores are 7, 7, 8, 8, 8, 6, 7, 8. And the score for the opponent. 7, 8, 9, 7, 8, 8, 5, 7, and 7. Finally, the score for the reviewer are 7, 8, 7, 8, 9, 8, 8, 8, 8, 7, and 6. So, okay, so we got 2 6. Any comments from the 6?
I will comment. So for the reporter, so your presentation and your report is really good.
But unfortunately, so during the discussion, you keep strong arguments, but it could be stronger. So therefore, there's a little bit lower grades. But it is not the main point. The main point on the grades is it answer directly to the questions, and also some questions you didn't answer. So that is the main drawback. Otherwise, you could at least get a 7 from me.
For the opponent, we have 5. Also you.
Okay. So for the opponent, so the 5, the main reason is from your discussion. So I think you put too much on, and also from the energy perspective, you didn't tell us what, why it is more has better advantage than the force analysis. And, you didn't bring in more insight, and therefore, so other discussed that what were discussed. That is the main drawback. So and a very strong drawback.
For the opponent, we got 4.8 and 1.9. So any comments about the high score? Yeah, if you wish. Okay.
Sorry about my comments. I'm really republic. I think we need to do this discussion in speed up and point out some questions. Although they didn't get the final conclusion mentioned by the Professor Rowe. We didn't come to the very key points. Anyway, I like the way we discussed the report. Thank you.
Okay, for the reviewer, 1.637 and several 8 and 1.9. So any comments about the 6? Yeah.
Yes. So for a reviewer, I give this list because the reporter has emphasized a lot about the scaling law, but you didn't mention anything about it. That's why I deduct.
Okay, so if there's no further comments, so I would like to thank all the reporter, opponent, and reviewer for this this morning's Physics 5. So let's give the big hand about this. Announced, so I think everybody can calculate the result by themselves. So I would like to close the Physics 5 this morning, and thanks everybody, thanks all the jurors and all 3 teams. So hope everybody can enjoy the lunch banquet prepared over there. And let me make a small remind that whenever you pick up your lunch, please wearing your mask. Try not to make a long conversation around the table. Yeah. Okay, thank you everybody. And we will have a closing ceremony starting from 2:30. So please come back and get seated. 2:15 or 2:20. Okay, thank you.